Okay, so do you have any questions about the last time? Not. Okay, so a reminder. Last time we found the green function of 3+1 wave equation, namely for, I would write it, we have solution of this wave equation as delta function on the right hand side. And it is given by 1/4πr, delta function of t minus r. And by the way, this green function can be written in the Lorentz invariant way, also Heaviside theta of t. So the first remark that we can write it in a Lorentz invariant way, namely we can write that it is theta Heaviside of t over 2 pi over 2 pi delta function of r squared, maybe t squared minus r squared. So why is it so? This is because we have a formula for the delta function of some f of a. So some f of x. And let us find this formula. So suppose that this function has a single zero at x0. So maybe we can write the general formula. Suppose that this function f has several zeros. F of x ends equal to 0. And let us integrate this delta function of f of x with arbitrary test function. So x ends zeros of n, zeros of f. Like this. So integral delta of f of x from minus infinity to plus infinity with some phi of x dx. So we can say that it is so it vanishes away from these points. So we can reduce this integral to sum over n, integral from xn minus epsilon to xn plus epsilon, delta of f(x), phi of x dx. And then we can change the integration variable. you can switch from x to f of x. So it will be the integral from uh, f of xn minus epsilon to f of xn plus epsilon delta of f phi of x dx. And d 1 over f prime df. And now, depending on the sign of this f, we should either switch limits of integration or leave them as is. So it will be sum over n sine of f prime of xn. Hmm? Yes. Hmm? No, we just don't consider functions for which it is not true. Because no, in principle we can do something like this, but no, probably it will just make no sense. So it's better to consider functions like this without any pathological things. So. For example, it can be single zero or pair of zeros. So in our case, it will be single zero in the domain of our interest. So since it is delta of f, it will give precisely the point where f equals to 0, so xn. So it will be 1 over f prime of xn times phi of xn. So in general, it is a sum of n phi of xn 1 over absolute value of f prime of xn. So looking at this formula, what can we say about delta of f of x? What does it equal to? So hmm? No, why? We have just computed the integral of this delta of x with arbitrary test function and see this result. So what can we say about uh, about the integrand? So if it was step function, we would have some integrals over some intervals of this phi of x. But we see that the answer depends only on phi of x in some points. So it depends on phi of x at the zeros of f. Hmm? No, could you say it again?
Delta function of f of x can be senior sine
Mm.
prime of
But why? I've already written everything as absolute value. So and what else? Mm, mm, no, mm, 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 yes, yes. So, good. Oh, is it the answer or? Hmm? Hmm? Uh, What f prime what? Oh, well, in principle, we can write arbitraries, uh, but the question is, how many terms in the sum will we have? Hmm? Oh, but what is uncountable? So it's just some n from, let us say that there are n n zeros of this function. Hmm? Oh, but what is times n? No, the question is what kind of generalized function gives a phi of xn? No, delta of xn is either 0 or hmm? Yes, yes, thanks. And of course we have some of this. So is it clear? Mm. So if you integrate delta of x minus xn with phi of x, it gives precisely phi of xn, and this is just prefactor. So, so is it okay? No. So, and here I just used this formula saying that delta of t squared minus r squared is 1 over r delta of t minus r, because in principle there is another delta function of t plus r, t plus r, but we know that it is 0 because t and r are both positive. So, so Is it okay? Mm. So hmm?
we understood that the f and the f prime of xn is different from the
Yes, of course. Like this formula suggests this. Because otherwise it is a not defined object. For example, delta of x squared is something not defined. So and, in our case it is true, of course, because derivative of t squared minus r squared is 1 over 2r. It's minus 2r. And, so is it okay? Okay, so, hmm? Literally this. So a delta of t squared minus maybe let us write no okay like this t squared minus r squared is 1 over 2r delta of t minus well r minus t plus 1 over 2r r plus t. If look at this as a function of r, and this term can be neglected because mm, because mm, yes. So we just take this formula and substitute here, and we see the original result. So d in dr of t squared minus r squared equals to minus 2r. So this is derivative of r. Yeah, as derivative of r squared. Hmm?
there is the multiplicity of the zero is one.
Hmm. Hmm? So a derivative should be a derivative of f in its zeros should be non-zero. Otherwise, it is not defined. But and it is visible from that formula, because if you have a zero in the denominator, then it's then in the end. Mm-hmm. Yes. Uh, mm. No, no. If its derivative vanishes somewhere, then we'll get this 1/0, and it means that this function is just not defined. So, uh, so we cannot consider delta of x squared. The only functions which are allowed are of this form. Hmm? No, no, no. What do you mean? Xn's are zeros of f. We know that if we want to compute this integral with arbitrary test function to understand what kind of generalized function we have, we need to integrate over the whole real line. Uh, this the parts of this integral which do not touch zeros of f will just vanish, because the delta function is zero in that points, and all the integrals around zeros of f should be considered. So here we write the sum over all zeros of f, because mm, in principle, yes. So we don't need it here, but we can consider, for example, a delta function of cosine. It will be the infinite series of delta functions, and it has well-defined Fourier transformation. And we actually saw it before. It was the delta function on a circle. We know it's Fourier series. So. So, uh, what? So, Are there any questions? Are there any questions? Phi is an arbitrary test function, so to be on the safe side, I will say that phi is infinitely differentiable function with compact support. So this should hold for any phi. And if some equality holds for any phi, then it holds for generalized functions in general, because generalized functions are functionals on this space. So if their parents with any function coincide, then they coincide by definition. So if you have some function that takes phi at points of xn with this coefficient, then it is by definition this generalized function. So, so is it clear, or do you still have some questions? Mm, mm, mm. So, for example, Mm, if you write some delta of ax, it will equal to 1 over absolute value of a delta of x. So, something like this. So, is this fine or not? And by the way, let me maybe tell a little bit more about properties of this delta functions and their derivatives. Mm, if it is something non-trivial, so So, for example, it can happen in some computation that we have a product of some function f of x times delta of x. Just a product of two of the usual function and generalized function. So, do you have any guess like what should it equal to? So if you want study this, we should do the same. Compute a pairing of this generalized function with arbitrary phi. Uh, yeah, maybe I'll do like this. So it is there is a delta function, so it should compute this expression at point x equals 0. So it will give phi of 0, f of 0, yeah, f of 0. So and what does it tell about the original function? So can we write any expression for it? y minus. Thanks. Yes. Because it does precisely what is written here. This pairing of f of x with phi of x gives phi of 0, and this is just simply factor. Oh, good. Okay. And for example, if we write x times delta of x, so what is x times delta of x? Mm-hmm. And but if we try to divide delta function by x, it will make no sense. Mm. It will be something undefined. Mm. So we can also ask another question. So it was about delta function. What happens if we write some nth derivative of delta function? So we need to do the same. We need to compute this pairing phi of x, f of x, delta nth of x. Hmm. So it's integral from minus to plus infinity dx phi of x f of x delta n of x. And this integral, so actually we could say that there is a definition of delta n's as a function that computes n minus 1 to the n times function that computes derivative of phi of x. But this definition is equivalent to saying that we just integrate this integral by parts n times. And then use the definition of the delta function. So it will be the integral dx and dy dx phi of x f of x delta n minus 1 of x equals and so on. So do this integration by parts n times. So it equals to integral from minus to plus infinity dx minus 1 to the n dy dx phi of x f of x delta of x. So it is minus 1 to the n dn over dxn phi of x f of x computed at x equals to 0. And now we can write a formula for the sense derivatives. By the way, do you know this formula? So it will be some sum. So how to compute an nth derivative of a product? Yes, thank you. So if you don't remember this formula and need to derive it, it can be done like this. This nth derivative of this nth derivative in x acts both on phi and f, and we can in principle introduce two derivatives that would act only on phi and only on f. So we can write it as d over d phi d over dx phi plus d over dx f to the power n. So derivative acting only on one of these functions, and then use a binomial formula for this sum. So the answer is that it is sum from m equals to 0 to n c n m phi m of x f maybe less how is better to write n minus m. Hmm? Binomial coefficients. So binomial coefficients. Do you write them like this or with this bracket notation? Bracket. So then it is maybe this one, right? So smaller number is on the bottom, right? Mm-hmm. Thank you. Yes. Mm-hmm. Okay, so now we see this, and we also need to remember the definition of nth derivative, or the delta function, that pairing of phi with delta delta n equals to minus 1 to the n phi n of 0, because of this integration by parts. So what if we remember this definition and try to write the formula for this product? So we already computed the pairing with arbitrary test function. So what is the answer for this product? So so let me write it. So it equals to what? So. Mm-hmm. 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 Yes. So minus 1 to the m, right? And delta m's of x, right? So there's such formula. So is it okay? So So in particular, we can look at this equality and ask what if we multiply x by delta prime of x? So x times delta prime of x. We can just take this identity and take its derivative. So x delta prime of x equals to minus delta of x. So there is this equality. It can be understood as either as derivative of this equality, or it can be derived in this way. Yeah, so this identities are useful if you want to compute something with delta functions, because it appears quite often that we have a delta function of some other argument, or we have some product of this kind. So, are there any questions about this? Probably I had some problems about delta functions and generalized functions in general. Mm. Okay, but I was telling this partially because I want to use such kind of identities in the computations. Okay, so can I go further, or do you have some questions, or something is still unclear? So, okay. Uh, So the computation I want to do is the following. So at the moment we know this green function in 3+1 dimensions, and in principle, if we want to compute it in 2 dimensions, we would need to do all the same computations with contour integrals and so on. And actually, these computations are a bit more complicated in 2 dimensions. But I want to use the same trick as we did for the heat equation. I want to reduce this 3+1 to 2+1. So I want to compute this green function for d equals 2. It will be a function of t, x, and y, 3 variables. Uh, so this is g equals 3. So, and what kind of formula should we have here? So if you have a green function of d equals 3, t, x, y, z. So how can we get this green function from this one? Yes, and so it's integral from minus infinity to plus infinity dz. And some geometric picture for this is the following. So we have some 3-dimensional space. Uh, mm, I'm trying to draw some part of the space. So three-dimensional gain function is a kind of a spherical wave that is emitted by a point at 0, and two-dimensional gain function is this cylindrical wave which is emitted by this infinite line located at point 0, 0 and going infinitely in z dimensions. So this integral represents the summation of all contributions from points of this line. Okay, so we have this formula now, and let us compute the integral. So so we need to integrate. So this g d equals 2 is integral from minus infinity to plus infinity dz 1 over 2 pi and delta function of t squared minus minus x squared minus y squared minus z squared. Yes, thank you. Here. So this will always be there. It cannot disappear. Now there is a question. Like, what happens if this expression this expression is less than 0? So it will vanish, right? Because this argument will always be negative. So we can write that there is this Heaviside theta of t. So it also contains a Heaviside theta of x squared of t squared minus x squared minus y squared. Right? Because if this is negative, then we have delta function of a negative argument all the time. Yes. So, and but if it is positive, we need to find a 0 in z, right? So, so it will be sum over z equals to plus minus a square root of this expression. So, so integral in z at 0 to pi. So it will be a sum of two delta functions at this point with the same prefactor. 1 over square root of t squared minus x squared minus y squared. Delta of z minus square root of t squared minus x squared minus y squared delta function of z plus square root of plus. And what does this integral equal to? So, this is some constant. Hmm? Yes. So well, let us write this constant. Uh, what coefficient should I put here? So what else should I write? Hmm? Well, so in principle we can put it, but what happens next? So what happens when you compute this integral? Yes. So times 2, and so it means that we just can cancel this 2 with this 2 in the denominator. And this is the answer for this d equals 2 gain function. Right? So we can also write it in the in kind of vector notation. We can write that it is heaviside theta of t, heaviside theta of t squared minus r squared divided by square root of t squared minus r squared. Right? And uh, let me think. No, it's fine as is. Also, we can rewrite this heaviside theta or product of this heaviside thetas using the fact that absolute value of r is positive and uh, and so t squared minus r squared positive means that either so actually so let me think. Actually, we didn't even need to write this no, in this notation we need to write this Heaviside theta. But if we have doubts, so in this notation it is unclear whether t is big positive or big negative. Like, is it greater than r or less than minus r? But if we try to write Heaviside theta of t minus r, knowing that t is positive, then it is enough to have just one Heaviside theta, t minus r over square root of t squared minus r squared. So it's an equivalent way of writing. Hmm?
T is a scalar and R is a vector.
No, scalar r is by definition absolute value of r, or the square root of r squared. Hmm? Is it fine? So, and, let us consider some example. Again, let us say that we have some source at 0. Namely, we consider this equation dt squared minus Laplacian of u equals to some phi of t times delta of r. And now, so let me separate this. So this u of t and r will be the integral over all times dt prime all r's, and we substitute this f times f of t prime and t prime delta of r prime times times this gain function. Here we said theta of t minus t prime plus minus absolute value of r minus r prime divided by square root. So this integral in r prime can be computed. It just puts r prime equals to 0. So we have this integral in dt prime f of t prime. Let us write for a moment this Heaviside theta of t minus t prime plus minus r prime minus r. And now we can remove this Heaviside theta and say that it is the integral from minus infinity to t prime plus r. And t plus t, t minus r, sorry. So the integral of dt prime f of t prime over square root of t minus t prime minus r squared. Squared. So this is so this r squared is again square of the length of r, and this is what I told the last time. Value of this u at the point r at time t depends not only on the value of source shifted by r to the past. Like it's not like it depends not only on a signal that was traveling precisely for a time r divided by velocity, which is 1. But it depends on this source at all previous times. Which means that if you have some speaker located at some point and will listen to the sound from the speaker, we will hear it even during the time when it is already off. So this function has this shape. And its decay when t prime goes to infinity has a form 1 over t prime. So it is not even exponential. It is something decaying quite slowly. In principle, we can compute all this in higher dimensions, and the answer always has this kind of form. Actually, this formula is similar to the green function of Laplace operator, because because for Laplace we had 1 over r to power d minus 2. So and here we should count also the time. So it is a 3-dimensional space in total. So it is so gain function of Laplace operator is 1 over r, and gain function of this wave equation is 1 over this Minkowski r, but also with heaviside theta. So and in higher dimensions, the answer looks similarly, but in that cases we will have some higher powers of this expression in the denominator. Sorry, is it d minus 2? Yeah. So it will be a power like like this power, and the problem is that such expression is singular on the whole surface when r squared minus t squared is 0, and this is some cone. So we also need to think about the definition of that function, and it is defined like nth derivative of such function that should be understood in the sense of generalized functions. But maybe it's just too much details about these functions. But maybe I think, or maybe it's too much details. So we can say, or maybe no. Let us maybe say a few words about such generalized functions. So, so the main question we should ask about this integral is whether it is convergent or not. Mm. So the integral we need to because there is something in the denominator. So the integral we need to compute is dt prime dr prime some f of t prime r prime. We said theta of t minus t prime minus r minus r prime. Over the square root. So let us look at this integral around the in the domain t is approximately t prime no, t prime is approximately t minus r minus r prime, because it is the domain where this denominator vanishes. So we can write it approximately. Yes, thank you. Yes. Mm, uh, mm, We want to study this domain when it goes to 0. So let me think. Mm, uh, when t prime is approximately this, then so this part can be approximated by absolute value of r minus r prime times 2. So it is some constant when we compute this integral in t prime. So and we can also shift this integration variable. So it will be the integral from so it will be the integral in d t prime tilde f of t minus r minus r prime plus t tilde r prime times heaviside theta of t tilde over square root of t tilde. So is it correct? Mm. Hmm? Yes.
Did you write brackets on your left?
Which brackets?
Vertical brackets.
No, it's just insertion of a comment that we are considering this this domain. So maybe if I put it in the box, it will be less ambiguous. Hmm? Mm, so the idea was to do some shift of t prime. Actually, sorry, it should be actually a minus t tilde, and here it's also minus t tilde. Maybe maybe I want to do it in this way. So t tilde is maybe let us parameterize t. T equals to t tilde equals to t minus r minus r prime minus t tilde. So is it fine? So what we need to say that the integral something times d t tilde over square root of t tilde is convergent. Hmm? No, I'm saying that so let us insert here this other factor times 2 square 2 r minus r prime. So I'm saying that this denominator can be written as a product of two factors. One of these factors vanishes, another equals to some finite number. Mm. Is it fine? Okay. So let us uh, since we have only square root singularity, this integral is convergent. So there are no problems with convergence in this case, right? Hmm? Uh, F, yes, in a sense it should not have some bad singularities which can interact with the singularities of the Green function. Yeah. Probably we could impose some conditions on this f, but better not to do because we can restrict it too much and uh, can rule out some useful cases. So, and otherwise it will be hard to prove that everything is correct, everything works. Mm. Ah, so once we see such kind of behavior, once we see such integrals with square root of t in the denominator, I wanted to say a few words about such thing which is called fractional derivatives. Probably I can erase this because we hopefully we remember this anyway. Uh, hmm? Yes. So uh, uh, let us let us take a function phi of x and uh, uh, compute the following object d mm, how to denote it. Let us call it d alpha d alpha phi, which is defined as the integral from d alpha phi of x is equal to integral from minus infinity to to x phi of x minus x prime dx prime over x minus x prime to power alpha. And this alpha can be from from 0 to 1. Well, in principle, phi is decaying fast enough. Maybe we can say that, maybe to be on the safe side, let's say that it is from 0 to 1. So, if this phi goes to 0 at minus infinity, and if it has no singularity, then this integral is convergent. It is some well-defined integral operator, right? So in other words, it can be written as d alpha phi equals to the convolution of theta of x minus x prime divided by x minus x prime. Well, no, let me write it like this. It's a convolution. Theta of x over x to power alpha, convolution with phi. So we know that if maybe I should ask this. So so if some function is given by a convolution of two other functions, what can we say about the Fourier images of these functions? Mm-hmm. Thanks. So we know that d alpha phi Fourier image equals to the Fourier image of theta of x over x to the alpha times Fourier image of phi. So we need to compute Fourier image of theta of x over x to the alpha. So. It is a notation for a function of x, but a convolution of these two. So it's a kind of integration variable. This convolution means, so if you write that some f equals to convolution of g of x, probably we can introduce some notation for, well, let me just write that there is some function, big F, big F here, and the definition of this function big F equals big F of x is theta of x over x to the alpha. So is it fine? No. Because a convolution of the two functions is a function that depends on some variable x. So by definition, f. So if some h equals to f convolution with phi, it means that h of x function h of x equals to the integral from minus to plus infinity dy f of x minus y phi of y. So the definition of the convolution. So, and so. Yes. Why not? So this integral terminates at x. It terminates at the point where x minus x prime becomes negative, when the argument of this function becomes negative. And this is precisely reproduced by this Heaviside theta.
But b divided with x prime.
But it is some variable. I can put here Cyrillic SHA, and it will be the same function. Was it the question, or was it a different question? Hmm? Mm, oh, sorry. Sorry. I actually wrote some function that does not depend on x. Sorry, I didn't understand this. Sorry. Is- Sorry, I was thinking probably about this theta, but it's not theta, it is phi. Yes. Sorry. Mm, mm. So, is everything fine? No. Mm, yeah. Thank you, and sorry. Okay, so now we need to find the Fourier image of this function. Uh, so Fourier image of f of p in the integral from minus infinity to plus infinity dx e to the minus I p x, and we can actually terminate this integral immediately. Write that it is an integral from 0 to plus infinity. Uh, 1 over x to the alpha. So it is in principle convergent, but not very well. So we would like to rotate the integration contour a little bit to see something familiar. Namely, so it is x plane. It is better to have exponential of negative argument. So it's better to integrate over, not over this line, but over this line. So exponential goes to 0 in this domain. So difference of these two integrals is this contour at infinity, and it goes to 0. So we can say that it is this we can say that there is a variable that variable x is parameterized by minus I times z, and now the z will go from 0 to plus infinity. So it is integral from 0 to plus infinity d minus iz e to minus z e to I pi over 2 times alpha. Because we are rotating in the clockwise direction, and we have x in the denominator. So times z to minus alpha. Right? Actually, sorry. Yes, it should be there. And sorry, I also forgot to say that. And I also forgot to do this. That this should be computed separately for positive and for negative p. Sorry. Yes, it is for positive p. So for positive p, it is like this. So it is p greater than 0. Pz, it is p greater than 0. And for p less than 0, it should be rotated in the opposite direction. From 0 to plus infinity, d of plus iz e to minus absolute value of p z e to minus I pi over 2 alpha z to minus alpha. Right? So is it fine? Okay. So could you say it again? Now, the question is what to do with this integral. So this integral should be computed differently for positive and for negative p. And I'm considering separately the case when p is greater than 0. In this case, contour should be rotated to the negative imaginary line. For p less than 0, it should be rotated to a positive imaginary line. So, but it will not be analytic at 0. And since all these functions work as integrable kernels, it is fine. I know in pencil. So could you say it again? Yes, of course. This is what I'm doing. But hmm? No, no, but which is zero in this x plane or in the p plane? Hmm? But it is this alpha is between 0 and 1. So dx over x to the alpha is d is 1 over 1 minus alpha d of x to 1 minus alpha over 1 minus alpha. So it means that this integral is convergent at 0. So so this contribution will be just 0. So we are considering only this case. So is it fine? So we should not care about this because we don't need to cut this integration domain in near 0. And any integrals around some small circles around 0 will be just differences of this x to 1 minus alpha computed at different points. And they will be 0 because alpha is from 0 to 1. So, good. Okay. Okay, so now we can rescale this integrals count all the powers. So so the first integral is so when p is greater than 0, it will be the so let us count the phase. It will be e to the minus I pi over 2 plus I pi alpha over 2. And then there will be a power of p, and it will be a p to alpha minus 1. No, it will be, yes. Probably this. Integral from 0 to plus infinity dz e to minus z z to minus alpha. P less than 0. So it will be e to
Now we have the sum of the e minus
where, could you say it?
this line.
Because there was a factor minus I here, and there was this factor coming from the integral. Yes. Okay, so this equals to I pi over 2 plus I p alpha over 2, and it will be absolute value of p to alpha minus 1 integral from 0 to plus infinity dz e to minus z to minus alpha. So and in total so, so this can be written as e to I pi over 2 alpha minus 1 times p to alpha minus 1 times a gamma function. And this gamma function is of 1 minus alpha. And here for p less than 0, it will be e to minus I pi over 2 alpha minus 1. So let us write absolute value of p of alpha minus 1 gamma of 1 minus alpha. So we can write this also in a different form. So we can say that for positive p it is written in this way. So we can write it as I p to power alpha minus 1 and for negative p actually the same, minus I p to alpha as ip times alpha minus 1. But we only need to say how to pass from one domain to another one. So this is this differs by a negative phase, which means that rotation.
Why in case that p is negative, we have e to the minus I pi over 2 alpha minus 1 and not plus?
Because we had to rotate in the opposite direction. So this was a picture for p greater than 0, and there is analogous picture for p less than 0. So for p less than 0, this integral should be closed in a different half plane. So we rotated into this direction. So this means that x equals to iz. So and all this z's, so z should be multiplied by e to the I pi over 2. And so z2 minus alpha is multiplied by this factor e2 minus I p over 2 alpha.
My problem is that over there, in the second line of this record, there is a sum, and it should be different.
Where? Sorry. It was about, yes. Sorry. So here it was a difference. So it should be difference here. Yes. Thank you. Okay, so we see this formulas are also multiplied by gamma of 1 minus alpha. Gamma of 1 minus alpha. So the question about a definition of this powers, of course, isn't there because it's not single valued function, but it can be read from here. So this root is this fractional power alpha minus 1 is defined such that the phase for positive p is this one, for negative p is this one. So if we want to write, if we want to draw a picture for some branch cut in this function, then we should send it to positive imaginary direction, saying that if we sit on this line, then IP to power alpha minus 1 is real, and then we perform analytic continuation to the real line and to positive real line and to negative real line, and getting this signs. Okay, so is it fine? Yeah. So, we have such a Fourier transform. The positive thing is that we see that it is some function analytic in the well, we can say in the lower half plane or in the whole plane without one cut removed, but it is some function.
It's minus
No, it is plus because it is itself negative on that real line. So we need to check that phases of this expression are fine. So if you say that it is real on the negative imaginary line, then it means that its phase, when we continue counterclockwise to positive half line, will be this, and it will be this if we continue to negative half line. So it is precisely this expression, right? So the point is that it is the same analytic function considered on positive and on negative half line. Is it fine? So, but now let us remember that the Fourier transform for function looks like this: phi of x equals to integral dp over 2 pi e to the I px phi tilde of p. So. And if we act with some derivative on this function, if we consider dx to the power n, then what we will get here? We will have ip to the power n phi of x phi tilde of p. So it is a derivative is proportional to a multiplication by ip to the power n, right? And so if you look, if we look at this formula and at this formula, we can conclude immediately that this that a fractional power of derivative, namely dx to power alpha minus 1, can be identified with this operator d alpha written here, divided by a gamma of 1 minus alpha. So in particular, if alpha equals to 1/2, we can say that dx to power minus 1/2 equals to 1 over square root of pi dx to minus 1/2 acting on f of x is 1 over square root of pi by definition. Integral from minus infinity to x dx prime f of x prime divided by square root of x minus x prime. And we can check, for example, by explicit integration that if we take two such derivatives, like some exercise. I check that dx minus 1/2 dx minus 1/2 acting on f equals to f. So there will be two explicit integrals. We need to change the order of integration and get something as a result. So. And if we don't take this derivative in x, then it is more or less clear from the definition of this fractional derivative that it is not quite symmetric. It's integral from minus infinity to x. It will mean that the action of two such derivatives will give the integral from minus infinity to x of f. So, and I was telling this to say that there are these generalized functions which look similar to this fractional derivatives, and such integral representation exists only for alpha between 0 and 1. Otherwise, it starts becoming divergent. And if we need to define something that has a higher power of x minus x prime, which will happen in this case in higher dimensions, it means that we should represent such derivative as a composition of a usual derivative taken several times, and this fractional derivative between 0 and 1. So okay. understand that if you try to put some large alpha and write this integral, it will be divergent. So, so for this one, everything works fine, but for in higher this higher dimensions, we will have precisely such kind of divergence, which should be understood in the sense of generalized functions, that we first take derivatives of a function we need to act on, and then act with some kernel with integrable singularity. Okay, maybe that's all. Do you have any questions? Hmm? Hmm? No, no. The rule is the following: that 2 pi appears every time you have integral in p. All integrals in coordinates and x-axis coordinate are without these factors. So it is. So there is also symmetric rule with square root of 2 pi everywhere, but I don't like it because there are some formulas where this rule is violated, and if we work with formalization when 2 pi appears only with momentum integrals, then it works for any formula. So it's just a measure of integration in the momentum space. Okay, so thanks for your attention. See you next week.